across different things, right? So right now, whatever we are seeing, this particular quantum and so many other things, if you're going to heard of big data or else machine learning, or else if you're going to talk about the AI, ML, and so many other things. So this quantum computing is right now is the future of this particular, whatever the technology which we are going to see. It is going to see the world in a very different way. How we can say that? How we are going to say that? What is the evidence for that? Now, let us understand several types of examples on this, how the quantum computing is coming into the picture here. So, and what is the fundamental nature or physical nature here, which has been built, that we are going to see in this particular today's session. So, students, if you're all ready, I'll just share my screen, right? I just want to confirm, everyone, any one of you, is my screen visible?
Yes.
Yeah, thank you so much. So, as the name indicates, it is quantum computing. What is meant by quantum? I feel why this word quantum is coming into the picture. Computing means what? Computation is happening, but what is this quantum? So, whenever we are going to talk about quantum, it is a phenomena, or it is a physical content or a concept of a matter that has been explained by using computation equipments. So here, quantum is nothing but a physical particle. Okay, and we are able to find out the relation between the quantum particles, the particles which are existing in the nature, physical particles which are existing in the nature, how the communication happens, generally happens with that, how it is different from the real computation. That is different. So in today's session, we are going to understand what are the quantum gates, and also we are going to study what is a single qubit circuit. Okay, and the quantum here, these are the topics which have been covered in this today's session. What are the quantum gates? What is the basic operation and reversibility? And we are going to also study the quantum gates types. In that, we are going to study quantum gates X, Y, and Z. Then H gate, Hartmann gate, and phase shift gate also we are going to cover. Then we are also going to cover the quantum circuits, how the quantum circuits have been formed. Then we are also going to see the single qubit circuit. These are all the things which we are going to study in today's session. So it has been clearly explained what is the agenda, students. Okay. Now let us start with what is quantum. Okay. Okay. So before going to this, we are going to start what is quantum computing and who was the father of this quantum computing. So we know that the basic computers or the classical computers are going to deal with if you're going to consider the MacBook or the supercomputer, everything deals with zeros and ones, right? But here the quantum computing deals with qubits. That is what is the difference. Then if they are going to deal with qubits, what is a qubit? Okay, I think you are all familiar with what is the bit, right? Yes. So what is a bit? Bit is nothing but 1 or 0. But what is a qubit here? They are talking about qubits, and this quantum computing is having qubits, right? Then before going further, we are also going to discuss who is the father of this quantum computing. He is David Deutsch. He is a theoretical physicist at University of Oxford. Okay, and he is called as the father of computing, quantum computing. What is this? He was working is nothing but he was working with the first quantum version of your Turing machine, okay, where it was able to do the quantum computing as well as simulate any physical systems. Simulation means it is going to create a new picture of the same one, and it is able to find out with the mathematical computations, we are able to find out whether it is working well or not. Simulation is going to happen. With that, he was working. So let us understand the difference between what is a qubit and a bit. Okay. Okay. Now, if you're going to see students, are you able to understand basics? Any response from the students? Okay, let me continue. Here, if you're going to see a classic bit, this is nothing but a bit this side. Bit can be either 0 or else a bit can be either 1, right? So, but a qubit is nothing but a different representation where it can be 1 and 0 at the same time. How this is going to happen? Okay, let us take an example. Let me suppose you went for a what is that? You went for one bakery, or else you want to purchase one, you went for a Pizza Hut. Okay, let me take a Pizza Hut. Okay, in that, you have ordered two different types of pizzas. Okay, one is a cheese pizza. The other one you have ordered is paneer pizza. Both you have ordered. One is a cheese pizza. The other one is paneer pizza you have ordered. Okay, and the person has packed these two pizzas in two different boxes, but the boxes look same. And from outside, you will not be able to identify which particular box has cheese one and which one is having paneer one. So if you're going to take the first box, it can also contain cheese one and also contain a paneer one, right? So that first box is playing a role of having a cheese pizza or else a paneer pizza, both. So here the position is nothing but it can be both one and 0 at the same time. So therefore, this is called as a qubit. Okay, this is called as a qubit. According to the laws of physics, quantum physics, a particle or a subatomic scale is there at the same position at both the times at the same time. So that is nothing but we are going to call it as 1 and 0. And here we are going to also talk about the specific phase that is nothing but superposition. Okay, smaller atoms. And here whenever we are going to talk about the physical particles, where a particle includes different types of electrons, atoms, and an atom can move with the electrons, and you are having photons, neutrons, everything inside an atom. We know that atom is the smallest entity in this world. Okay. In that atom, we have all this. Electrons are there, protons are there, neutrons are there. Okay. Now, based upon all these three, I can decide my position. That is what nothing but your superposition. Let us understand much more deeper way on all these things. Okay. Now you can see here the representation of what makes the qubit more powerful, why it is very powerful, because it is having peculiarly three different properties. Okay, three different properties. The first one is interference, second one is entanglement, and the third one is superposition. Because of these three properties, we are saying the qubits are very powerful and than your classical bits. You can see here, whenever you're having the manipulating the information on computers, you can see that we are going to use logic gates. Okay, so here what happens, the different combination of logic gates will give you different results. You'll be generally finding AND gate, OR gate, NAT gate, like this. You'll be finding the many number of gates. So the combination of all those will form the output in a generally manipulating the values in the computers. Okay, so here the properties of a qubit are three things. What is interference, entanglement, and superposition. That's the reason they are very powerful. Let us understand all these three features in a way. Okay, first one is nothing but superposition. What is meant by superposition? I am present here, I am also present some other place. Multiple places I am present as the same entity, as the same person. So how it possible? How nothing but called as superpositioning. Okay. Now, when a particular atom is present in multiple places with the same values, same content and all, then we are going to call it as a superposition. So let us take an example. Let us take an example here. We are going to take a glass of water, and in that I'm going to fill oil and water. Okay, oil and water. Can we separate oil and water here? Definitely, yes. Yes, oil can be separated from water. Though I'm going to stir it and again just check, wait for some time and check, still I can find out oil drops are separated and as well as water drops are separated, but still I can locate oil at different positions, but at the same unit. It is the same unit. So therefore, here the superposition means the same thing is existing at a different places is nothing but called as superpositioning. Exist in multiple state at once. Okay. Now imagine here if you're going to see the formation, mixed qubits, that is neither 1 or 0, but both. Okay, until it has been separated. So here we can consider some more examples also. If you're going to consider measuring the spinning a coin, okay, whenever you're going to spin a coin, what happens? It is going to spin, okay, and we don't know what could be the outcome of that. It can be 1 or 0, right? So but whenever it is spinning, it can be anything. So it can be 1 and 0 at a particular point of time until we know that one. So here they were telling about another example here. Another example here is nothing but, if you're going to take this example of a classic bit binary system, you're having 0 and 1. Okay. Now, here you're going to change this particular states. We are going to find out, we are able to spin this particular sphere. And what happens? We doesn't know what is going to happen at the end until the state, whatever is going to happen. So, but what is that here? Whenever suppose, let me suppose here, if you're going to consider, now if you're going to consider here, uh, uh, the bits, whatever you're going to talk about, the qubits and all, here what is happening, I'm able to position at the same place. How it is able to interact, how it is able to communicate. Let me suppose after spinning, okay, now I'm having one coin in one box, okay, one box at let me suppose we are playing a game, okay, we are playing here in Chennai also. I'm playing, and I'm also playing in another place at Hyderabad or Bangalore or Pune or anywhere else. Okay, now what happens when I am spinning? Okay, I'm getting 0. But when the people, other people are spinning at different place, also are going to get the same value. That is nothing but called as entanglement. Okay, what is nothing but? It is nothing but called as, ma'am, am I clear now? Hello?
It's clear. It's clear.
Yeah, yeah. Thank you, sir. So if you're going to say, now, as I told you here, we are going to, though we are going to be there at different positions, different places, when I'm spinning that, I'm going to get a same value, 0. If I'm getting a head, there also I'm going to get a head. If I'm getting a tail, there also I'm going to get a tail over there. So how it is going to happen? Here, that is nothing but there is an alignment. There is a communication. That communication, we are going to call it as entanglement. Or else we are going to say that how this is going to form. Now here I have taken two examples to explain what is entanglement. So one example here shows that two boxes are there. Okay, in these two boxes, ma'am, you want me to give a definition of entanglement? Okay, I'll just repeat the definition of an entanglement. It is nothing but quantum physics, where it is when two particles are entangled. So you can determine the spin of both of them just by looking at one of them. One is going to be having the head, the other one also will be having head. How it is happening? It is nothing but based upon the spin, which there is an angle, there is a relation. That relation we are going to call it as entanglement. Yeah, definitely. Let us understand this by using an example here. Okay. Now, as we are seeing here, I'm having two boxes. One box is having a red ball. The other box is having two red balls. Okay. Now, but I'm having many other balls also. I'm having a blue ball. I'm having a green ball and all. One ball is given to Alice. The other ball is been given to Bob. Okay. Two balls have been given. Okay. Alice doesn't know which color ball is there in this particular box. And even the Bob doesn't know what is the color of ball which is present in this box. Both doesn't know. But unexpectedly, because of entanglement, if I have given Alice a red ball, okay, if I have given Alice a red ball, the same red ball will be given for Bob also. That is nothing but a relation. How the relation is forming, how there is a communication, that is only that relation or the communication which is having between the particles, we are going to call it as entanglement. Okay, now let us understand one more example here. Okay, now after your school hours, okay, what is happening after your school hours? You went to your home. Okay, and if your mother is there or not at your home, how you're able to observe that? By seeing her only her slippers, right? Her slippers. By seeing that, you can easily understand whether your mom is there or not. It is not at all required that your mom should be present. Okay, physically she is also not present also, but by identifying whether she is present or not, you can identify by using the slippers itself. So therefore, here there is certain relationship. There is a communication that is happening between the particles. That communication is nothing but called as entanglement. So how I can say that there is a communication? The communication is nothing but generally what happens in a physical world or else in a computing world. If there is a communication means it is through Wi-Fi or else through phone or through the internet connection only. A physical system is actually present. But here the physical system is nothing but the atoms, electrons, protons, neutrons, whichever are there, which communicate to each other to find out the relation between the between the objects. So that relation we are going to call it as entanglement. Now, if you're going to take this example of this particular entanglement, here if you're going to see this cat, okay, and it is finding a path, right? Okay, it is finding a path here to send this particular wool. Okay, so if it has to find out this path which has been framed here, how it is able to do that? Okay, now it is going to send it, and then it is able to find out the relation here. How it is able to communicate? It is only by sending that one. So the relation, how it has been explained, is nothing but called as entanglement. As we have discussed, there is a superposition. That means at different places, I'll be getting the same value. That is nothing but superposition. Entanglement means the relation which exists between the particles at one place with another place. I'm calling it as entanglement. Then let us talk about how the communication is happening. That is nothing but your interference. Okay, this interference, how it is going to happen? Okay, now here, because an atom, okay, let us go, interference is nothing but whenever I'm going to start communicating, okay, with one particular atom to another particular atom, and it goes on communicating, and it reaches that particular place, and the same state is going to be observed here, right? Though it is very, very far also, still you will be finding the same state at a different place. That is what is the speciality of your qubits. So this, how it is going to happen? Let us take an example here. If you're going to have pool of water, okay? Let us take, if you're going to have a pool of water, okay? Now, whenever you're going to have water, If you're going to throw a stone into the water, what happens? It is going to generate multiple number of waves, right? That is what here you have given, multiple number of waves. These waves, whatever you are going to find, if it is interacting, if it is, there can be two things. One is a constructive wave, the other one is a destructive wave. If it is constructive wave, it is going to expand much. If two waves are interpolated at one place, then it is going to become much more bigger. Okay, the wave becomes much more bigger. Suppose if it is a destructive wave, whenever it is going to interpolate, it is going to spoil, it is going to break. Okay, that is nothing but called as destructive interference. So here we are having wave. These waves, whenever the atoms are going to form, okay, they become bigger, so that they communicate to each other. So let us see how it is going to happen. For this is one of the important experiment to understand the interference. In this, we have taken, these are the electrons, okay, and we are having certain wall, okay. You can see this, there is a wall. With an electron shooter, I am shooting multiple number of electrons. Okay, with the electron gun, I am shooting multiple number of electrons onto this wall. Okay, if I'm shooting multiple electrons onto this wall, what is happening here? To this wall, actually, this is the wall. You can see here, students. This is the wall which is there. Here, this is the wall. Onto this wall, I'm passing many number of shooting with the electron gun. Okay, and these are the I have kept certain stoppages, or else I have separated that wall between that particular gap. So it has to, electron has to hit the wall. That is how we have taken here. Now, whenever I have taken the electrons which are passing here, okay, how they are representing after certain point, you can see this side. Okay, these electrons are forming beams. You can see that these are forming waves. These waves are helping them to communicate. Actually, it has to go only one electron has to hit this electron which is actually hit. Okay, this should be the expected result. But what is that? It is actually happening. These electrons are communicating and forming the waves like this. So this is forming the photons. Light sources are happening, and because of this, you can find this. This is what is the actual result is happening. This is the example of interference. Interference. Is this clear? Any doubts in these points? Okay. So we are going to just revise all these things. So we have seen, okay. We have seen what is a qubit. We have seen the three important features of a qubit. First one is superposition. Second one is entanglement. Third one is interference, right? Okay. Now, the last important, what is that? Already we have discussed these all features, right? We have seen the superposition. That means the same state is at different place. Though I'm having it at different locations also, I'm there as the same. That is nothing but called as superpositioning. Entanglement, the angle, how the communication is going to happen is nothing but entanglement. Then whenever the electrons are shooted, when the electrons or the atoms are shooted, what is that happening? It is forming the waves where they start communicating to the different other electrons whichever are there. And the last one is teleportation. Teleportation means whenever the wave started expanding, right, they communicate, they teleport the information. That is what is called as teleportation. You can see that. Now let us take this example, whatever is being given here. Here I am having a qubit. This is one qubit and this is another qubit. Okay. You can see that whenever I am spinning this one, you can see this is nothing but your entanglement which is happening. This is what the spin is happening between the electrons. So whenever I'm spinning them, What is that happening? You can see that we'll just separate this particular arrows. So this is the up arrow, this is the down arrow, which has been passed actually in the first one. Okay. But after spinning them, after entangling them, that means the angle has been changed. You can see that it has been moved in a different direction. And this has moved in a different direction. So actual states are this one. But after entanglement, this is what is going to happen. Separate, though they are at different states, determining to other reveals the state of the other by using this vice versa concept. If you want, it can be the same. If you want, it can be the reverse. Anything can be possible because these are qubits. Okay. Now let us start with your quantum gates. So as we have seen here, what is a teleportation? This is nothing but a communication which is happening between the qubits. Okay. Now we will see the simple gates which have been given here. Okay. And the gates which we are having are nothing but we are having H gate and we are having C naught gate and we are having poly gates. Right? So we can see that what happens, we know that a qubit can be either 1 or else 0, okay, and 0 or else 1, right? So here, so let us understand first the classic gates, then we are going to discuss the quantum gates, okay? Just a moment. Yeah. So let us discuss this one, students. Here, if you're going to see the classic gates, whatever we are having the classic gates as AND gate, OR gate, NOT gate, and combination of and NOT, we are going to form a NAND gate. Here, this is forming NOT gate and OR gate combination. We are getting OR gate, NOR gate, and XOR gate and XNOR gate. Like this, we are having several number of classic gates. How it is that you can see that when an AND gate is applied, if you're having two inputs, A and B, okay? So how it is that if you're going to pass 0, 0, then it is going to be 0. Only the expression when both are 1, okay? Then only it is true, right? 1 means true, 1 means true. So for A input, for this input, we are giving 1. For this input, we are giving 1. Then only the output will be 1. So that is being explained by this AND gate. If both are 1, it is 1. Therefore, it is multiplication. A and B. Okay. Next, you are having OR gate. Here what happens? If any of the values, if from the two inputs, if any one is 1 also, then also I'll be 1. So here you can see that in this particular OR gate, you are having 0, 1, 1, 1, 0, 1, 1, 1, 1. So in all these three cases, one is there at least one time, right? So therefore, this is OR gate. So therefore, x is equivalent to a plus b. This is addition operation. This is a multiplication operation. Okay. Next one is a NOT gate. Here what happens? Whenever I'm saying yes, you're going to say no. Okay. Whenever I'm saying no, you're going to say yes. That is what is a NOT gate. It is opposite. Okay. Next one is a NAND gate. As I told you, it is a combination of both AND gate and a NOT gate. So how the expression will be? Here it is going to say opposite of your AND gate. Okay. So if 1, 1 is there, then only it is 0. In all the remaining cases, it is 1. Okay. Opposite of your AND gate. Not AND. So therefore, 1, 1 is 0. Remaining all the cases, it is 1. Coming to the NOR gate, here what happens? Here 0, 0 is 1 in all the opposite of your OR gate. So therefore it is 0, 0 is 1. In all the remaining cases, it is zeros. Okay. Now coming to the XOR gate, here what happens? Both should not be the same. Either it should not be 0, it should be 0 and 1 or 1 and 0. Then only I'm true. In all the remaining cases, I'm false. So both should not be same is the concept of XOR gate. Then coming to the XNOR gate, it is opposite of your XOR gate. Both should be same, then only I am 1. The remaining cases I am zeros. Okay. So therefore, these are the classic gates. So here, what is that we are giving? We are giving two inputs. Okay, A and B, and with which I am getting a Y. Here we are having both. Okay, in qubits, you'll be finding by the simplest change of 1, 0 and 1, we'll be getting the X gate. And plus and minus, you'll be getting a Z gate. And H gate is for specific 0 plus 1 and 1 to minus, we'll be getting a H gate. So generally, how you're going to represent a gate here? This is what is your qubit representation. You're going to write the qubit as this dash and this is indicating 0. In the same way, if you're having 1 here, you'll be having okay, ma'am. I'll just explain what is a gate. Okay. Okay. So students, what is a gate is really a question that has to be
I will
answered.
explain.
Yes, sir.
I will explain. A gate is this. For example, if you are in a school, I'm talking to a student. If you are in a school, there are two gates that are allowed. First gate is your parents have to allow you to come to the school. Your parents will have to allow you to come to the school. If your parents do not allow, the school cannot take you in there inside the school. Second gate is that of the school gate. One is your parent gate, that is your both the parents have to allow you to go to that particular school. Second is having the parents allowed you to come to the school, you are entering a particular school, not any school you like. Your parent may be wanting to go to any school, but that's a different thing. First of all, they have to allow. That is gate one. Let us call it as a P gate. Second gate is that of the school. A particular school, say S1, has to allow you. Your friend may have gone to another school, S2. The third friend must have gone to another school, S3, etc. So the allowing the first gate is your parents should allow you to go to some school, gate one, and a particular school will have to allow you to get inside their school. So this is the concept of gates. Okay, the same thing happens in all other areas. I have tried to put it as simple as I can. Lakshmiji, go ahead.
Yes, sir.
Thank you.
Thank you so much, sir. Hope the students have understood the concept of gate. As sir told, it is nothing but a permission or else acceptance that is making the people to do certain things. If you're going to take the example, what else the sir has given, the parents are first accepting that, then after that, the school also has to accept. So in the same way, these particular gates are actually useful to construct the circuits. Now, where and all you are going to find these gates? Whenever, if you're going to see the motherboard of your computer system has a logical circuit where, let me suppose, if you want to open an application, like let us consider the application whichever we are seeing a front, that is nothing but Zoom application. Now, whenever you're opening the particular application, whenever you are opening that application, automatically the permission will be going, that whatever the link has been there, that is going tracking that to the motherboard, checking whether that particular app is there, whether it requires any updates and all. Everything is being operated. Okay, that communication, whatever is happening, that all is nothing but which is being based upon the logical circuit which is there on your motherboard. So what is a motherboard? It is having a circuit, combination of various number of gates. So these gates are connected to each other, communicating yes or no, 1 or 0. That is what is happening. Okay, 1 or 0, it is happening continuously and it is forming a circuit. Whenever it is saying yes, okay, then only the application is getting opened. Are you able to understand this one? So it is a huge circuit, but though the motherboard is very small, but it has many number of electronical components which are there, which is able to make use of forming a circuit and changing the values wherever it is required. System can understand only one thing, students. It is either 0 or 1 in a computing system. But in a quantum computing, it can be anything because we doesn't know what is going to happen. Right? So here also we are having certain gates which helps us to communicate to the, which is helping us to form a circuit here. Okay, so what are the gates which are helping us to form a circuit is nothing but we are having certain basic gates which is called as a hard mart gate. First one, H gate we are going to call, Z gate, and also poly gates we are having. Okay, and C naught gate. So these are the 4 types of gates which we are going to study in today's session. So now here, one more thing I want to tell you, students. Here they have given that a qubit. Okay, a qubit it can be 1 or a 0. What is this 50%? It is nothing but your probability. Probability that the qubit value will be 1 is 50%. Probability that qubit value will be 0 is 50%. It can be half anything. It can be 50% of 1, 50% probability of getting 1, 50% probability of getting 0. So that is this. Therefore, here it has been given that 50% is nothing but your probability. So the quantum gates here are, whichever you are seeing right now, are nothing but X, Y, Z and H gate. Okay. And the last one is nothing but your C naught gate. We will see each one of them in a very detailed way, with each one with an example also. Okay. Okay. So
పడుకున్నా మేడం ఇంత డెప్తగా
What is that?
So the next one we are having, as I told you, in polygates, we are having X gate, Y gate and Z gate. So what is the X gate, Y gate and Z gate are nothing but whenever you are having the sphere, here the atom or the electron, whatever it is going to sphere, right? So whenever it is going to sphere, it can be in x-axis, it can be in y-axis, or it can be in z-axis. Suppose if it is on x-axis, then you will be having this value, so 0. This is nothing but your matrix representation of your X gate. Okay, matrix representation of your X gate. Let me suppose if it is If it is on the y-axis, then you'll be having this representation. If it is on the z-axis, then this will be the representation. Okay. And you are going to also have one more gate called as phase gate. It is changing from one position to another position. Let me suppose, as we have already discussed at certain examples, like the position, if I'm 0, right? Okay, if in my place I'm having head, okay, in another place also I should get head, right? As I told you, that because of the superposition. Now whenever I'm talking about the superposition, the phase, if it is falling, if it is about to fall tail, it has to change its phase, right? So therefore there is a phase gate which is going to shift actually. So that gate we are going to call it as a phase gate. So these are the basic gates which we are going to study in today's session. Okay, so let us go with one state at a time.
Matrix, just a minute. There was a question on matrix representation.
Yes.
Matrix, first of all, means quantities arranged in arrays or columns. Arrays are horizontal and columns are vertical. For example, if you go to a hotel, you might ask for one thing to eat and one thing to drink. Supposing you want to eat some dish and drink, say, coffee or tea. So the eating dish and the drinking dish are two different things, correct? Now, the eating dish will have a certain cost per unit, and the drinking dish will have another cost per minute, per 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 unit. That is per piece. Supposing you ask for one coffee and one eating dish, okay, you will have to pay the bill. So you put the eating dish and the drinking a coffee along the column, and you can put the cost of the coffee and eating dish in the horizontal column. When you multiply the number in the number in the column to the number in the row, you will get one coffee into its cost, and other thing is one eating dish into its cost. You have to add it. Okay, that will give you the bill. So creation of a bill requires matrix multiplication, and this matrix multiplication means numbers arranged in rows or columns. If the rows are arranged such that they represent cost, then the columns will represent the items and the rows will represent the quantity. Suppose the cost is one dimension and the name of the dish is another dimension. So your bill gets generated by a multiplication, and that is what it means. Okay. Thank you very much. Yeah. Lakshmi, proceed.
Yes, sir. Thank you so much, sir.
Yeah.
So here, as sir has explained correctly, it is nothing but a way of representing the values on both the axes, x-axis and y-axis. If you want to represent that using bits, then we are going to say that that is present or not by using this particular uh, matrix representation. Let me suppose if you're having a salesperson, okay, who wants to travel from one location to another location. Okay, generally what happens, the salesperson will be traveling from multiple locations. So if he is going to start from Delhi, Mumbai, Chennai, Bangalore and Pune, okay, suppose if he has visited that particular city, he will be marking it as 1. Suppose he has not visited that city, he is going to marking it as 0. Okay, so that is that representation, whichever we are going to say yes or no. Yes means 1, no means 0. Okay, so that representation we are representing in it 2 by 2 matrix or a 3 by 3 matrix. That is nothing but if you're going to increase the number of sizes, the number of rows and number of columns, it increases, then you're going to form this matrix representation. Okay, so here we are going to study all this, the phases by the different gates by using the matrix representation which is given here. The first gate which we are going to study is here, NOT gate, quality. So here you can see that poly gate, X gate, this is an X gate. Here, what is that happening? If you're going to give 0, you can see that 0 is been given here. Okay, you're going to represent the 0, and this is the form of your polygate. Okay, here performs a bit flip, rotates, negates, and the qubits. Here, whenever you're passing 1, you're going to get a 0. Whenever you're going to pass 0, you're going to get a 1. Okay, so this is the basic example of a X gate here. If you're passing 1, you're going to get the outcome as 0. If you're passing 0, you're going to get the outcome as 1. Okay, now here, I think then we are having the hard mud gate. Okay, here what is that you are having? If suppose this is a circuit here, we are having X gate and H gate. Okay, we are passing 0 here. Then this is the representation. It can be XH or HX, or it can be XH or XX. So these are the 4 different representations that can be formed using the hard mud gate. Okay, whenever you're going to pass 0 to the H gate, what is that you're going to get? You will be getting 0 plus 1 divided by root 2. Why we are getting this one is nothing but here it is saying that in the previous slide also I have shown you when a H gate is there, it can be either, you can see that Hadamard gate, it can be either 1 or 0. If you're going to pass 0, it can be either 1 or 0. Therefore, we are representing that it is half of it. Okay. Therefore, we are representing that. Therefore, the value here will be like this. 0 plus 1 divided by root 2. It can be either 0 or it can be 1. Divided by root 2 is the outcome of your hard mode gate when you have given the input as 0. Suppose you have given the input as 1, then your hard mode gate output will be 0 minus 1 by root 2. To represent that, it is a 1 input. Okay. You can please note down the value, students. When a 0 input is given to the gate, H gate, you will be getting the output as 0 plus 1 divided by root 2. Suppose if you have given 1 as the input to the hard mode gate, you will be getting the value as 0 minus 1 by root 2. Okay. Sir, you want me to give a break for 5 minutes or else you want me to continue?
Yeah, I think a break will work. Break. Let me just introduce one thing. Uh, Shaka Hadamard. Shaka Hadamard was a French mathematician who lived in 19th and 20th century, and he is no more. And this particular gate, Shaka Hadamard, is named after him. The last D is not to be pronounced if you want to be French specific. If you pronounce D also, nothing matters. Okay, so it is known after him. The beauty of this gate is it adds and divides by root 2 and subtracts and divides by root 2. This is a particular gate very specific to quantum computing. For school students, they should know that there are various kinds of gates. For example, you have a school gate that allows many children at the same time. There's another gate called as a wicket gate. In a wicket gate, only one person can enter. There is a circle where only one person enters, and you have to push the gate so that you come out the other gate. So not more than one person can enter in what is called as a wicket gate, WICKET. So just so there are many gates to enter a school, here is a particular gate that is useful for quantum computation, and it is called as the Hadamard gate. Thank you very much. Now I think a break you can announce, and we'll proceed. Yeah. Yeah, you would like to take a break and come back? Yeah.
So can we start? Hello?
We'll start.
Yes, sir. Sir, can I share my screen?
Yeah.
So students, we have started with gates. So we are going to discuss the four different gates. What is nothing but your poly gate, which is named after one more physicist, that is nothing but polyphere, and Hadamard gate, C-naught gate, and phase shift gate. So here, I'll just give some introduction about, already we have discussed it about this gate, but let me give you an example how this is going to work. Suppose, what is that? If you're going to switch off a particular light, okay? If you're going to switch off a particular light, what is that? You're going to use the switch button. So when it is, if you want to switch on, you're going to switch on that one. You're going to use that particular control and you're going to just switch on that and it is going to work. Suppose if you want to give 0, that means if it is off, then you want to switch off. Then you're going to again click that button and you're going to make the control to 1. So where it is going to become 0 and then it is going to become 1. So here if it is 1, you want to make it 0. 0, you want to make it 1. If it is on, you want to make it off. If it is off, you want to make it on. At that time, you're going to use this first one, polygate, X gate, which we have seen. Now, next one, which we have seen, the another example is Hadamard gate. Here, as I told you, it is just an as we have discussed here, how it is going to work. And these are the certain circuits which have been given here. Here, these are the circuits. Okay. So here, already it has been explained that how this particular, if you're going to give the input as 0, this will be the output. That means here, 0 plus 1 by Kate 0 plus Kate 1 by root 2. If it is Kate 1 is being given as a input, then you'll be getting Kate 0 minus Kate 1 divided by root 2. Okay. So here, the example of this particular Hadamard gate is nothing but if you're going to flip a coin, we doesn't know what could be the output. Right? It can be either head or a tail at a particular point of time. But here, whenever while it is spinning, we doesn't know anything. So therefore, this is just representing your qubit. Therefore, this is called as a Hadamard gate. Next gate which we are going to see is nothing but your C-naught gate. In this C-naught gate, it is just opposite of it. Whenever you have given the qubit as 0, you'll be getting the output as 1. Okay, it is flipped. Okay, then if you have given it as a 1, it is going to be 0. Okay, so how it is going to work? Let me suppose if you're having a fan remote. Nowadays you're having fans where you're getting a remote. Suppose if you're going to use a remote, either switch on or switch off your fan. So suppose if it is on, you want to switch off, right? Then suppose if it is off, you want to switch on. Okay, so just like that, this particular gate is going to work. Okay, C-naught gate, controlled NOT gate. You want to do opposite of it. Okay, now we are having the next one, measurement function. Why it is being measured? Because you can see that you have given the control. That means either 0 input or Kate 0 or Kate 1 you have given as a input. Then what will be the output of that one? 0 or 1. That is measured by using this measurement function. This is how the representation is there. Okay, this is a meter representation. Actually, either it can be 0 or 1 will be represented by using this measurement function. So how this measurement is going to happen? Because of the entanglement, okay, because of the communication, interference, because of this two, the position can be either 0 or 1. Okay, so that can be decided by using this particular measurement function. Next we are having is phase shift gate. Here, what is that you're going to say is nothing but I'm going to shift from one particular phase to another phase. So here, whenever we are going to talk about the phase shift, it is going to change from one position to another position by shifting the phase from 1 to 0 or 0 to 1. So that happens here in the phase shift. phase shift phase. So let us see certain examples on this. Shifting the phases by using this particular e power I theta. That is going to measure the phase and it is going to shift the phase from the existing position to the another position. That is what is your phase shift gate. Okay, let us take the example, students. How a qubit is represented as a vector. So this is gate 0 is nothing but 1, 0. Gate 1 is 0 and 1. Please note down, students. I request you all to note down this one. A qubit is represented as a vector. And you can see that gate 0 is nothing but 1, 0. Gate 1 is 0 and 1. And this representation, we are going to call it as matrix representation. Okay, definitely. I will explain one more time the measurement function. So measurement function, so as I told you in this example, when I was teaching this one, measurement function, if suppose you have given 0, okay, we doesn't know whether it is 0 or 1, right? So how it is being measured? How we can decide either is 0 or 1? So that function that is being decided by using this by measurement function. Let me suppose if I want to find out, as we have seen in the previous case also. Okay, let me suppose if you have given you, we have taken example of a pizza box. Okay, pizza box. How are you going to measure that one? I want to find out whether that is a cheese pizza or else it is a paneer pizza. Okay, I want to find out that. How are you going to measure that one? How I can decide that that is a paneer pizza or else cheese pizza? I can check the weight may be differing for both of them, right? The weight for a pizza, cheese pizza will be different and the weight for a paneer pizza will be different. Probably I am expecting that cheese will be lighter than the paneer one. So therefore, based upon the weight, which I'm going to keep on my hand and check, I can find out, I can approximately guess what could be the pizza type inside that. Okay, let me suppose based upon that, the probability here. I can expect that the probability that it is a paneer pizza based upon the weight. So that function, whatever you're going to try to guess, is nothing but your measurement function. Hope it is clear now. Now here, the communication, what happens is nothing but based upon the entanglement, based upon the spin, whichever you're going to create for the atoms to electrons to communicate is nothing but your measurement function. Okay, let us, I think so, we can proceed further. Okay, so representing a qubit as a vector, you can see that it is a gate 0, we are going to call it as 1, 0, and gate 1, we are going to call it as 0, 1. This is a matrix representation. Let us take the first one, poly X gate. In this, you can see that X is being taken as 0, 1 and 1, 0. Suppose you have given if the qubit is gate 0, okay, you're saying the qubit is gate 0, then if an X gate is being applied, okay, this gate X, so 0 is nothing but what? 1, 0. So therefore, and X is nothing but 0, 1, 1, 0. So therefore, we have taken X value and as well as gate 0 also. Okay, both are being taken. Multiply these two. Okay, multiply these two. Therefore, after that, you're going to get the value as 0, 1, which is nothing but what? 0, 1 is 1. Therefore, we have written it as gate 1. How to multiply this one? 0 into 1 plus 1 into 0. 0 into 1 is 0 plus 1 into 0 is 0. Therefore, the first value is 0. Okay. Next one. 1 into 1 is 1 plus 0 into 0 is 0. 1 plus 0, therefore it is 1. So 0, 1 is 0, 1 is 1. Therefore, when you have given the input as gate 0, I am getting it as 1. It flips the state. It is initially the output, the qubit is gate 0, but we are getting it as gate 1. Now in the second case, if you have given gate 1, okay, qubit as gate 1. So X gate is been applied here, X gate 1. So what is X? It is 0, 1, 1, 0 into gate 1, that is 0, 1 we have given. So multiply these two matrices, 0 into 0 plus 1 into 1. Therefore, here it is 1. 1 into 0 plus 0 into 1, it is 0. So this 1, 0 is your gate 0. Therefore, you are getting 0 here. I request the teachers to check whether the students are able to follow this, and if it is understood, then I can proceed. Okay, ma'am. Okay, I'll just explain that. Phase shift gate.
They need to understand the concept of phase first. Phase means the following. For example, the moon has phases, meaning there is one cycle of the moon around the earth, that is 28 day, that is a certain number of days. So we call all this, the first day of the moon, second day, third. So the way the moon presents itself partly to us over the first 15 days, these are the 15 phases. Similarly, on the other, the Krishna Paksha, the moon will go the other way around. So totally there are 28 different phases of the moon. Another example of the concept of phase is a human being is born, it's a baby, then it becomes a little child, then it becomes a youngster, then it becomes a middle-aged person, then it becomes old like me, and then finally die. This is called as a phase of an individual. Here we are talking about the same thing. We are talking about the phase shift, meaning change in the phase, change in the phase. Change in the phase does not mean the situation is changing. It's just going from one phase. Let's say you are a young person and then you become a middle-aged person or an old-age person. This is called as a phase shift. This particular gate helps us in allowing the phase shift to happen. Why I need to do the phase shifting is I need a particular measurement, and that particular measurement is necessary that I apply a specific amount of phase shift that is required here. Thank you. Yeah, proceed.
Yes, sir. Thank you so much, sir.
Hmm.
I request the teachers to check whether the students have understood this qubit as a vector and a polygate, so that I'll proceed for the next two gates.
Yeah.
Okay. Now coming to the next one, hard mud gate. In this hard mud gate, you can see that the representation of a hard mud gate is been given as 1 by root 2 into 1, 1, 1 minus 1. So suppose if you have given qubit as gate 0, then how this is going to work is nothing but 1 by root 2 into 1, 1, 1, 1 minus 1 into what is gate 0? It is 1, 0. Okay, 1, 0. Then just multiply this matrix, 2 cross 2 matrix into this vector matrix. So it is 1 into 1 plus 1 into 0. Therefore, it is 1. 1 into 1 plus minus 1 into 0 is 0. Therefore, it is 1. So, therefore, you're getting the output as, if you have given qubit as 0, the output is, and applied on the H gate, then you will be getting the output as 1 by root 2 into 1, 1. Okay. So, this is a superposition of 0 and 1. Then coming to the qubit 1, you have given a gate 1 as an input. Then you will be getting 1 by root 2, 1, 1, 1 minus. So therefore, into multiplied with 0, 1. So whenever you're going to multiply this 2 cross 2 matrix into this 2 cross 1 matrix, you'll be getting 1 into 0 plus 1 into 1. You'll be getting the first one. 1 into 0 plus minus 1 into 1, you're going to get minus 1. Here the value is minus 1. 1 minus 1. Okay. So here the superposition will be in this way. You're getting the, whenever we have given the input as 1 and hard mode gate is applied, then you're going to get this output. Yes, students, can I proceed?
I think so. I think so. It's a simple multiplication. Gates, when we convert from one to the other, we just multiply the rows and the columns. Rows and the columns multiplication that is required, and that is all. Nothing more than that. What the gates do is to transform a variable. It transforms a variable means you have, for example, raw rice, and it turns into a cooked rice. Okay, that is a transformation. How does the transformation occur? By applying heat to the rice in water. I take rice, put it in water, put it on the fire, and it becomes rice, something like that. The gate simply means that. That is something that changes the nature of the variable from one to the other. You are a young person, you become an old person. You are a child, you become an adult. That is a change in phase. Okay. Similarly, these are all simple multiplications involving not very big numbers. Okay. So just understand that. Thank you. Go ahead.
Yes, sir. Next gate which we are going to look is nothing but a C0 gate, controlled NOT gate. Here we are having the C0 gate is represented like this, where it is a 4 cross 4 matrix. Okay. And you can see that the target gate is being given here. The state is being given as 1, 0. Here you can see that 1, 0 is being given. And whenever we have C0 gate with 1, 0, then you can see the representation 0, 0, 1, 0. And whenever you're going to multiply this 4 cross 4 matrix, that is nothing but your C0 matrix with your state matrix, that is nothing but 1, 0 matrix, then you're going to get this value. So just multiply 1 into 0 plus 0 into 0 plus 0 into 1 plus 0 into 0, which is going to result this first row into this column. Okay, you're getting 0. Again, the second row into this single column, you'll be getting 0. This third row into this column, you're going to again get 0. And here, the fourth row into this column, therefore you're going to get 1. So this representation is 1, 1. Okay. Can I proceed?
Yeah, proceed.
So you can see that polygates, already we have seen that whenever you're going to give 0 as an input, you're going to get it as 1. Suppose if it is 1, it is going to become 0. And the matrix representation also we have seen here. Okay.
Input 0, X.
Yeah. Next, we are having polygate Y gate. So in this Y gate, what is that it is going to happen here? You're going to see why it is called as a Y gate. As I told you, if we are going to have Y axis. Whenever you're going to have the state, while adding a phase of I, okay, it rotates qubit to the Y axis. Okay. So that there is a change in the axis at that point, then we are going to get this particular Y gate. So the representation is Y is equivalent to 0 minus I 0. Okay, in place of 1, we are having I. Okay, because of the change in the shift. So therefore, here is suppose you have given the input as, okay, C0 gate. Okay, ma'am.
No.
See, C0 gate, as you are seeing here, it is a 4 cross 4 representation. This is the representation of your C0. Okay. Suppose you have given 1, 0. This is the state 1, 0. 1, 0 gate you have given. So 1, 0 gate, this is the value. of your 10 gate, and this is the value of your 11 gate. So here 11 gate you have 10 you have given, therefore this is the value here. So whenever we have multiplied C naught with 10 state, what is that we are doing? 1 into 0, first row with this column we are multiplying. So 1 into 0 plus 0 into 0 plus 0 into 1 plus 0 into 0. Therefore, you are getting 0 here. In the same way, we are multiplying each row with this column. So therefore, this representation we are getting, which is nothing but a 1-1 representation. It is a 1-1 representation. As we are having Kate 0, right? Kate 0 is 1, 0, whereas Kate 1 is 0, 1. In the same way, Kate 1, 0 is this value 0, 0, 1, 0. Kate 1, 1 is 0, 0, 1, 0. 0, 0, 0, 1. Any doubts still?
Proceed. I think we should proceed. Then we'll come back.
Okay, sir. Next, we have seen the Y gate. In this Y gate, suppose you have given the input as 0, then you can see that 0i, I0 is multiplied with 1, 0. You're going to get it as 0i. Okay. Then suppose if you have given the input as 1, which is nothing but 0, 1. So multiply your Y gate, whatever you're having this Y gate with 0, 1, which is nothing but minus I into 0. So you can see that whenever it is I of 1, this is I is nothing but your position, y-axis value. Okay. Then state I with a phase of I. State 0 with a phase of I, we are going to change. As sir has already explained, it is nothing but change. Based upon time period, you can consider his as your time period and we are going to change according to that. The last gate here in the poly gates is nothing but your Z gate. So here the Z gate is nothing but it rotates the qubit around the Z axis in the below sphere. So 0 remains 0 and 1 becomes minus 1. Okay. So here the matrix representation is 1, 0 and 0, 1.
Around the Z.
So let us take the example. Suppose you have given the input as 0, Kate 0, which is 1, 0. Multiplying with 1, 0, 0 minus 1, you're going to get 1, 0. So 1 into 1 plus 0 into 0, you're getting 1. 0 into 1 plus minus 1 into 0, going to get 0. So therefore, 0 is getting Kate 0, you're getting the same value, which is Kate 0. Suppose if you have given Kate 1, 0, 1. So here what happens? 1 into 0 plus 0 into 1 is 0. 0 into 0 is 0 and minus 1 into 1 is minus 1. Therefore, here you're getting minus 1. So these are the matrix representations and how the phases are going to multiply each with values we have understood. So this is what is the explanation summary of your 3 gate poly gates. X, this is the matrix represent, it is going to flip. Y, based upon the state of a phase, you can see that phase change is going to happen. Now here in the Z case, 1, 0, 0 minus 1 flips the phase. Okay. Phase of your existing state. Okay. That it is going to change. Only the change of state changes here, phase changes here. Now here some more examples have been given and explained about the hard-mart gate and all. So in this example, what is that? We are able to see a source where we are getting this light. Okay. Now here we have given one, we are just checking whether it is the light is either reflecting or else it is transmitted. Okay. That is what we are able to find out.
Yeah. Just a minute here. Here, a little bit of physics comes into the picture. What happens in this Hadamard gate is, notice that the light is coming from source A and it gets reflected. When it gets reflected, the phase change happens. Realize that light is a wave. Whatever phases it is bringing, in the process of reflection, the phase changes. Okay, phase changes by 90 degrees, and that is what is used here. The photon reflected with 50% chance, but when it is transmitted, the phase does not change. When transmitted, the phase does not change. When it is reflected, only the phase changes. Physics has a role here in determining what Hadamard gate does. Similar to what we do in polarization is, in polarization, the light will be blocked partly or fully depending on the orientation of one polarizer with respect to the other polarizer. That is not mathematics, that is the physics part. Similarly, in this Hadamard gate, you see that the photon gets reflected. When light gets reflected from any other surface, its phase changes. Phase changes means it turns by 90 degrees. This you have done when you do Brewster's law and other things. If you have done optics at early level, you will understand. If you do not understand this immediately, do not worry. When you learn good physics, you will understand it in your 10th or 11th. Thank you. Proceed.
So as sir have explained it clearly, it is nothing but
Hmm.
a Hadamard gate. It can be realized using two photon sources. We are having source A and a source B. And we are having a beam splitter is also being used, okay, in a photonic quantum computing setup. Okay, now here you can see that based upon the properties which we are having on photons and based upon the polarization and direction, okay, we can see that there is a change. If you are going to have a two detectors here, a beam splitter is a great example here. And what happens? What is that it is doing? Creating two orthogonal states, either it is 0, 1 or 1, 0. It is able to check 50% chances are there, either it can be reflected or transmitted. So we have kept two detectors here, A and B, again detector A and detector B, to check the output direction behind the splitter. Either it is passing either it is transmitting or else it is reflecting back. So these observations are there in this particular phase. Now let us check another example on this particular hard mode model, where we are having demonstrating the superpositioning using a hard mode gate. You can see that we are having again source A and source B again, and from one only we are passing the light here, and we are having two different beam splitters which we have used. And you can see that the whether you can see that how it has been a detector, whether it is a reflection is happening in path A, path 1, path 2, and path 4, path 3. You can see that how the reflection is happening and how the transmission is happening is being detected in this particular example. So here, if we allow the photons to continue to travel, placing two perfect mirrors in their path. Here, whatever you are seeing, the blue one is nothing but your mirror. Okay. And then a beam splitter this interferences the pattern with which will emerge. And you can see that a classical probability is again used to detect we are installing a detector A and B, which is going to find out the quantum interference leads to photons. Now, in this particular case, what is that you're going to see is nothing but we have again installed, according to the classical probability theory, we have 50% chance of detecting a photon, either A or B, or else it can happen interference, it can be photon to emerge A particularly. So this is going to happen in this particular detector. So here, this is being explained by this Hartmart principle of Hartmart gate. Okay. Can I go further, students? If you have any doubts, you can post it in the chat box in this. Now let us understand this particular gates. Here we are having a classical computer, 0 and 1. Okay, where the classical computer is going to say only either 0 or 1. Here is a small circuit being given here, quantum computer. Okay, now you can see that 0, 1. Okay, and you can see that there is a H gate, there is a X gate, there is a Z gate, and there is a H gate again here. Okay, this one. Okay, now let me, I request all the students to just note down this picture, because I'm giving a small quiz here where you have to answer these all questions. Can you please note down this one?
Note it down as it is and understand that learning anything new is not a soft process, it is a hard process, and there is a pain in the head, and you have to learn to associate with it. Climbing a tree is not easy, but when you climb a tree, then
One.
you have a chance of being saved from a animal which cannot climb a tree. Otherwise, you will be completely eaten up. Similarly, climbing a mountain is a process and it requires hard work. But when you reach the top of the mountain, you see a beautiful view which the people who have not climbed the mountain will not be able to see. It is as simple as that. Okay. Learn to negotiate with difficulty.
Some students or something are asking me to show the previous slide. Previous slide is this one, okay? And you're having this one. Which one you wanted? Is this slide okay? Now the first question, suppose if 0 is, okay? If I have given 0 as an input, I'm getting 1. What is this particular gate called? What is this gate where I'm giving the input as 0 and getting it as 1? Absolutely correct. It is X gate. Then coming to the next one, if suppose I have given, if suppose I have given 0, please see this one. Please see the circuit which has been given. 0 and X, which is resulting it to 1. And from 1, it is resulting that I'm having a H. And what will be the final condition here? When I have given 1 for the H, what is the final condition I'm going to get? How it is going to see here?
Ma'am, 0.
You can see here. Please see the circuit here. Please see the circuit here. What is that we are giving? 0 as an input. Okay. And it is going to like this. You can see this. It is going like this. It is going to 1. Okay. From 1, it is going to H. What is the final condition here? What is the final condition here? You can see here, please see the circuit and answer the question. We have started with 0. We are going to the X gate, right? This is the X gate, which is resulting it to 1. Okay. When I'm having 1, passing 1, and I'm going the H gate, then I'm getting what? What I'm getting? Minus. Absolutely correct. We are getting minus here. The final condition we are getting is minus. Okay. Please see the circuit. Don't think about your previous all slides, whatever we have discussed. Okay. Now, can you answer the next question? Absolutely correct. It is a H gate. If you're going to go with 0, okay, and we are getting plus as the output, then which gate we are passing? It is H gate. Okay, next one is Z gate. Absolutely correct. The next question, next answer is also Z gate. So here we are giving 0 as an input and we are passing that to X and we are getting 1. Okay, and we are getting H. We are going to go to H and we are getting minus. And from minus dash we are applying so that we are getting plus. That is nothing but your Z gate. Correct. And the last one, what is the output for the last condition? What is the answer for the last question? Fifth question. We are starting with 0.
To H.
X,
H.
X gate. Okay. X to H. Right? H. Then from H to Z. From Z to H again. And Z to X. What will be the output? It's 1. Absolutely correct. So it is 1 here. Okay. Hope you all have understood this circuit diagram and we have answered all these questions here. Is this clear?
Good. It's a slow process, but you will learn. You will learn. Learn to negotiate with difficulty.
So you can see it is a
Grow
very,
when
very
you
simple.
learn to negotiate with difficulty. Otherwise, you don't. Thank you.
You can see this, it is a last circuit is little little complicated one. You can see that we have started with 0, passing with X, and it immediately went to H. And from H, we went to Z, Z from H, H to X. Okay, then the output is 1. Okay. Okay. Now, how we have to construct this particular quantum circuits? Let us understand this constructing the quantum circuit. What is the steps we are having is nothing but understanding the components. So whenever we are going to talk about this particular understanding the constructing the quantum circuit, right? So first we have to understand what are the required components, whether we require X gate, whether we require Y gate, whether we require H gate. First, we have to understand that. So whether we require qubits, quantum gates, measurement. So what type of measurement? Either different quantum states into the classical bits. So first we have to understand all the components. The second step, choose the number of qubits. So how we are going to decide that one? So decide how many qubits are required for your problem. Okay. Maybe you may require 2 bits or else you may require 3 bits that you're going to decide qubits. Okay. So 1 qubit for basic operation, 2 or more qubits for if you're applying entanglement, or if you're using controlled gates, then you're going to go for 2 or more qubits. Okay. Basically, if you're using a single operation, you will be going for 1 qubit. Next, initializing the qubits. So initializing the qubits is nothing but you're going to specify what is gate 0, gate 1. You're going to specify that. Then applying the step 4 is applying the quantum gates. So here you'll be applying what are the quantum gates we have studied? H gate, poly gates, C0 gate, and phase shift gates. So these 4 will be the basic gates which are used for you to build your quantum circuit. So these gates we are going to apply. Next one is measurement. So adding the measurement at the end of the circuit, okay? So what to understand measuring the superpositioning, okay? So because we want the same representation, same state at the different places, then what is the probabilistic condition? What is the probability? That can be measured by using the defining the function here. And the last one is simulate or execute this particular circuit. So here we are going to create by using the Qiskit. It is a Python program, Python code where we are going to create the circuits. So with the Qiskit models, we are going to real quantum computers to run a circuit and get the results. That we can do by using the simulation or executing the circuit manually. So these are the 6 steps which are involved for
Send
constructing a
please,
quantum circuit.
2 pages quiz. Please have it.
Okay. Now this is a simple circuit which has been given here. So here we have given a gate 0 and this is a H gate we have given, and this is nothing but your C0 which has been applied here. In the same way, you have given multiple C0 function, C0s are there and as well as H gates are there. Okay, where it is resulting in a circuit form. Okay. This is the example you can see here. Initializing with either 0, 0, 0 or 1, 1, 1, you're going to initialize. Then you're going to have the superpositioning by using your H gate. We are superpositioning it. Suppose if you want to change from one particular state to another, then you're going to apply this X gate. Okay, right? Then suppose entanglement, that is nothing but you're going to apply the C0 gate here and rotate by using the phase shifting gate. And you're going to measure the output here. Either if it goes like this, then you're going to have the measurement. If it goes like this, it is going to find the measurement and it is going to check the measurement here. Here, measurement is nothing but entanglement. We are going to check. Superpositioning and entanglement together will be measured here.
1 minute. I just want to interject saying that when you're talking about the circuits and quantum circuits, you are basically learning how you have already learned how to add, subtract, multiply, divide, take square root, raise to the power, etc. Right, in simple mathematics. This is very similar to that. This is not exactly the same. It is similar, and not to be afraid. If you have taken a long time to do the basic operations, this will not take much time, but understand this as the result of operations. When you add some quantity to some other quantity, you will get a third quantity. When you subtract from some quantity from another quantity, you get some other quantity. So we are talking just about that. All the superposition, entanglement, and measurements, etc., are as simple processes as addition, subtraction, multiplication, division, taking square root, squaring, etc., or a combination of these. Not to be afraid of it. If mathematics scares you, you need to come out of that scare. There is no alternative. If mathematics scares you, you have to push yourself out of that scare. Otherwise, you will stuck there only. Thank you very much.
Thank you.
Learning is a hard process. Learning is a hard process. You need to learn to negotiate. Otherwise, you will never climb. Thank you.
Thank you so much, sir. Now, this is one of the example of a single qubit circuit. Single qubit is nothing but only one operation. One single qubit will be given as an input. Okay, you can see that here we have given a single qubit. Okay, and here you can see that we are having H gate, C naught, and X gate. So therefore, this is called as a single qubit gate. Okay, suppose if you are having two qubit gates, then you can see that here this particular C naught gate will be involved, and then it is going to give the input from here also. It is changing the value and it is giving the input here. So then when you are having two of the C naught gates, then you will be, because C naught requires two inputs, right? Whereas your single operation requires, X gate requires a single input. Okay, so therefore here what happens, if you want two qubit gates, these are the two qubit gates. Okay, and here we are having a single qubit gate. This is single qubit gate. Later, you can see how the measurement is being checked by using this entanglement and superposition. Okay, so let us last but not the least, we are going to start with certain keywords which we have discussed in this particular session. Okay, so first I'm conducting two different things, students. One is a assembling, that is scrambling. The other one is a crossword puzzle. Can you please give the answers quickly? First one is qubits, right? Second one. Okay,
Qubit.
second one, I will say it is reversibility. Third one.
Good.
Third one. Very
Good.
good.
Fantastic. Great.
Absolutely correct. Superpositioning.
Superposition.
Next one.
Very easy. Entanglement.
Very good. Next one.
Chitra madam, your kids are great. Yeah. Simple. Next is very simple.
I did not
Start
get
with the
this one.
reversible.
It is not circuits, it is circuits. Okay, circuits, correct?
Circuit.
It's
Circuits.
correct. Hardmard, correct. Poly, correct. And the last one?
Pauli. Last one, there is no I there. Last one is
Last one?
Pauli.
Phase shift.
Phase shift.
Phase shift.
Yeah.
Okay?
It is difficult because you do not know what phase is.
Yes,
Shift, perhaps you know, so
right.
don't worry. To get progressively familiar is important.
Okay. Now, the same keywords are used here to find, to fill this particular crossword puzzle. Okay. The same keywords are being
Crossword,
given.
great.
What is the sixth one?
The basic
Cross.
quantum information.
The basic unit of quantum information. First one.
Basic quantum preparation that rotates the phase of the
Right? Qubits, correct?
Not.
A
Good.
property of quantum system allowing particles to link states even over distances. Even over distances. Second one. It is superposition. Right? Okay, then the quantum state where a particle can exist in multiple states is simultaneously, right? Right? Reversibility. Quantum entanglement, a collection of quantum gates that perform unitary transformations on qubits. Students, I don't have any other words. We have used only those words which have been already discussed in the session. And fifth one,
I request students to form their own crosswords and their own, the mashed up word, their own, instead of depending on what Madam Lakshmi has given. Create your own and give it to your friends. Okay, that will help you know the word better. To know means to know the contents well, correctly.
eighth one is poly,
Create
madam.
your own quotes and send it to give it to the coordinator. They will share with me. Yeah.
Eighth one is poly, ma'am, because a type of quantum operator named after physicist. Poly is also a physicist. Okay. So before winding up, I'll just show you the answers here. You can see
Yeah.
entanglement. 3 is superposition. I'm sorry, is that visible? 6 one is phase shift, qubits, circuits, reversibility, gates, hardware, quantum, poly. Okay. So these are the answers for the crossword puzzle. Thank you all students for giving me certain opportunity to discuss this future computers which are going to be
If you want to fight a war, you need to know the terrain. If you want to fight a war, you need to know the terrain. If you want to cook a dish, you must know the kitchen. If you want to cook a dish, you must know the kitchen and kitchen utensils. This is what Lakshmi is trying to tell us. So get familiar with the words, and the fear of these words will disappear quickly. Thank you.
Thank you, sir. Thank you all the schools which have been participated in this particular program, and hope it is a knowledgeful session for you all. We have understood certain gates and we have understood certain mathematical concepts behind each gate which is involved in quantum computers. Thank you so much.